Ouais. Oui, là, donc vous m'entendez ou pas? Ce stress. Et on me voit bien là? On est bien? On me voit.
Je suis Sonia Fornatier, professeure à Paris-Cité et au Lila. J'ai l'honneur de présider ces jurys pour la soutenance des thèses de Léna Jossé, ici présente, sur la détection 3D d'assemblage minéralogique par SR-μXCT dans un échantillon de l'astéroïde de Ryugu, étude multi-analytique de leur formation et évolution. Donc, thèse qui a été faite sous la direction de Rosario Brunetto, qui est le directeur de thèse et chercheur de recherche ici à l'IAS, Alice Aléon Compagnie, co-encadrante, maîtresse de conférences à l'IAS et à l'Université Paris-Saclay, et Zélia Guéné, qui est astronome adjointe à l'IAS, Université Paris-Saclay. Donc, les jurys composés de Frédéric Monnier, qui est en ligne, professeur des universités à l'Institut de physique des globes de Paris, Université Paris-Cité. Tahar Hamouda, qui est professeur des universités au laboratoire Magma et Vulcan à l'Université Clermont-Auvergne. Et Romy Anna, qui est enseignante-chercheuse à Jackson School of Geoscience, University of Texas. Et enfin Mathieu Gensch, qui est professeur à l'Imperial College of London. Et bon, sans hésiter, on va commencer. Donc, Léna, c'est à vous. Vous avez 45-50 minutes à peu près.
Okay. So thank you everyone for being here today for listening to my PhD defense. So about the detection of mineral assemblages in a Ryugu sample. So before going into the Ryugu asteroid, let's have a brief overview of the solar system formation. So all the planetary bodies were formed in the accretion disk in the early beginning of our solar system, made of gas, dust, and ice, depending on their location on the solar system. So the particles start to accrete to form larger and larger particles, reaching the size of what we call the planetesimals of a few hundred of kilometers in size. Some of the planetesimals suffered differentiation process due to the heating of the radioactive aluminum-26 radioactive decay. So the matter melts, and then it results in planetesimals which has layers with a core, mantle, and crust. These planetesimals lost a lot of information of the primitive matter from which they form. Some other planetesimals, didn't suffer such global differentiation and global process, and these are what we call the primitive bodies. But among them, some processes, they suffered still some processes, such as the thermal metamorphism, which is the change of the mineralogy due to the increase of the temperatures. There are also the aqueous alterations, which concern the body that contain the ice, and with the increase of the temperature, the ice will melt and transform the mineralogy. And there are some more physical processes that can either fragment the surface of the body or totally disrupt planetesimals. And these are impacts. And the impacts can also form what we call the asteroid families. We also have meteorites, which are space rock coming from space and found on Earth. And among them, we have the achondrites, which are coming from the differentiated bodies, and we have the chondrites, which are coming from the primitive bodies. And so the chondrites are made of 4 main components: metal, chondrules, refractory inclusions, which are the first solid to form in the solar system, and matrix. And depending on the proportion of each of the components, we can subdivide the chondrites into different types, and among them we have the CI chondrites, which are made mainly on matrix. They contain also organic matter, and they also contain other minerals such as carbonates, sulfides, oxides. And all this mineralogy is typical from low temperatures aqueous alterations below 100 degrees. CI chondrites are also rich in water and volatile elements, and they also have distinct isotopic anomalies. And all of that supports their formation in the outer solar part of the solar system, beyond Jupiter orbit and beyond the H2O and CO2 ice lines. So CI chondrites have a secondary mineralogy. However, they are still the most primitive because they have an elemental composition close to the sun protosphere. So they appear to be the best meteorites to observe and to analyze the primitive matter from our early solar system. However, they are really rare. 6 meteorites are today known in our catalog, and among them we have Orgueil, which is the main mass. And they also, because they are meteorites, they also contain terrestrial contamination. And these are issues that can be overcome by return sample mission, especially Hayabusa 2, which sampled Ryugu asteroid. Ryugu is a 1 kilometer rubble pile asteroid. And so it is a rubble pile because it is thought to have formed through the reaccumulations of fragments after the disruption of the larger body. It is a CB type asteroid, so it is a primitive asteroid, and it is also a near-Earth asteroid. So it means, as you can see on this video here, it means that the orbit of Ryugu is very close to the orbit of Earth. So it is accessible to us. And so for all these reasons, it was the target of Hayabusa 2 missions led by the Japanese Space Agency called JAXA. So Hayabusa 2 was launched in 2014, and they performed 2 sample collections on the surface and the subsurface of Ryugu. And as you can see here, this video that shows the touchdown to collect the samples. And then samples were returned on Earth in December 2020. So these samples are free of terrestrial contaminations, and they offers us a very great opportunity to study the primitive matter in the context of Ryugu asteroid. So what do we know so far about this return sample is that here is a cut coming from 1 grain of Ryugu, and what we see is that the main component is the matrix, which is a mix of phyllosilicates and organic matter. So it's the dark gray here. We also find some carbonates, sulfides, oxides. Sometimes we also have phosphate. And sometimes we also have more primitive minerals, such as anhydrosilicates, phosphide, or refractory inclusions. Also, the isotopic anomalies, as you can see here on this plot, looking at the iron to titanium, Ryugu appears very similar to the CI chondrites, such as the minerals. They are all very similar. And so altogether, the scientific community is now trying to build a consistent scenario for both Ryugu and also its parent body evolution and formation. So what you have here is the Sun, Earth, Mars main asteroid belt and Jupiter. And so it is thought that the parent body of Ryugu was formed beyond Jupiter's orbit. Then it thought to have been migrated toward the main asteroid belt 5 to 10 million years after solar system formation. And then here, the parent body of Ryugu was disrupted, and then Ryugu formed here, such as the other Polana-Eulalia asteroid family a billion years ago. And then Ryugu became a near-Earth asteroid and close to the Earth. So I told you that Ryugu has a secondary mineralogy. However, there are heterogeneous samples. We observe some distinct mineral assemblages, also called distinct lithologies. And those lithologies in Ryugu are mainly characterized by their mineralogy, their elemental composition. As you can see here, you have a NIROM map with delimited lithologies, and also some spectroscopic characteristic. One other good parameter to study the lithologies are also physical properties, grain size, or porosity. Distinct lithologies on Ryugu is mainly found in the form of clasts or fragments. And this is why we call these samples breccia samples. The clasts are, so as you can see here on the left, you have, so the clasts are from tens to hundreds of micron in size, and they usually show clear boundaries. Oh, sorry. Oh. So among the lithologies, we found, for example, more altered lithologies, which shows the presence of carbonate and phosphate, and sometimes we observed less altered lithologies that contains anhydrosilicates and metal. And all these lithologies are all adjoined to each other, which testify the complexity of such samples and their complexity, evolution, and formation. And the origin of such brecciated textures is mainly associated to the brecciation process, which is the mechanical rock mixing of rock of different fragments coming from the different location on the parent body that had suffered different degree of aqueous alteration. But also other origins have been proposed, such as an initial heterogeneity in the accretion process, such as a different ice to rock ratio or different mineral proportions. And recently, another study have proposed an origins that is a subsequent chemical or physical process, such as the alteration front, which can also lead to formation of new lithology and distinct lithologies. So this brings me to the general scientific question of my study: how are distinct lithologies formed on Ryugu? So to answer such a scientific question, usually the previous studies are performed on artificially produced 2D surfaces. However, it means that we lost a bit of matter because we have to cut the surface, or it implies some destruction. And as we saw, samples are very rare and fragile. A new technique to overcome this issue is the X-ray computed tomography, XCT, which is the 3D methods that enable to look at the inside of the interior of the sample without any destructions. However, so far, the CT images and the XCT datasets need subjective human interpretation. So today, in this work, and during my PhD, I have developed a user-independent 3D data processing method to analyze millimeter-sized sample, to look and to detect lithologies in the sample, to characterize their distribution in 3D on a larger scale, and then I was able to perform and to choose a representative surface to perform further analysis and to obtain better constraint on these lithologies. And so altogether, the 3D analysis plus the 2D analysis allowed me to build a consistent formation and evolution scenario for the lithologies on a Ryugu sample. Sorry. So I mainly used the A0159 sample, which is coming from the chamber A, so was sampled on the surface of Ryugu. It is a millimeter-sized sample, as you can see here, and then it offers the better chance to find lithologies. And during my thesis, I also study orgueil samples because they are very similar to Ryugu. They are porous, fragile, they are rich in matrix. And I use millimeter-sized sample to perform and to develop tests to produce 2D surfaces. So as I already introduced to you, XCT is the 3D technique that enables to observe the interior of the samples. So it uses the capacity of light, the capacity of matter to absorb X-rays. So the principle is to send an X-ray beam through our sample and to analyze the flux at the exit as in the form of the projection. So this is the absorption along the line of sight of this beam. And if you rotate the sample, you can acquire multiple projections that can be then reconstructed to result in what we call the CT images, so stack of CT images in which we can see the interior of the sample. And these stacked CT images can be used to obtain a 3D model of our sample and to study it in 3D. So XCT can be used using an internal light source, so we call it laboratory-based instrument, but we can use it also using a synchrotron radiation that is created in synchrotron facilities, such as in Soleil synchrotron in Saint-Aubin. And so the synchrotron radiations allows a high brilliance of the flux, and it also allows a higher resolution for faster acquisitions compared to the laboratory-based instrument. And also, synchrotron radiations enable us to choose a specific energy to analyze the sample compared to a laboratory-based instrument, which are polychromatic and which results in artifacts in the CT, more artifacts in the CT images. So for the sample A0159 SR micro-XCT dataset, it was acquired on the Psyche beamline at an energy of 25 keV, which enables to have a voxel size of 1.3 micron. So as I told you, I also use 2D techniques to analyze the sample after having this 3D characterization. So I use the xenon plasma focused ion beam, which enables me to produce 2D surfaces of my sample. So the principle is to send a xenon, ionized xenon flux to remove the matter of the sample. And this was performed in collaboration with the Laboratoire Magma et Volcan. And all the procedure for this, for the ablation of the 2D surfaces was developed on an ergoid sample. I also performed scanning electron microscopy coupled with energy dispersive X-ray spectroscopy to analyze the elemental composition of the sample and to obtain high-resolution density electronic images. So the principle is to send an electron beam which will interact with the matter, and then the matter will send X-ray, and depending on the energy of the X-ray, we have the elemental composition. The maps of this work were acquired at the museum in Paris at an energy of 15 keV. And I also analyzed the surface using the Fourier transform infrared hyperspectral imaging spectroscopy, which enables me to study the molecular composition. So here the principle is to send a light, infrared light, which will interact with the vibrational mode properties of the molecules. And then depending on the energy, we have access to the molecular compositions. And so here I use the near to mid-infrared range. So now that we have our XCT dataset of A0159, how can we use this CT dataset to analyze the minerals assemblages? So we have to know first that CT images are made of voxels, which are 3D pixels of a size 1.3 microns, and each voxel has a specific value, one unique value. This value can be called the linear attenuation coefficient and depend on the density of the material that is inside this voxel. So denser is the material, higher will be the attenuation, and higher will be the lag value, and brighter it appears here. So one very common and well-used method is to analyze each voxel at a time. So here I'll call it voxel by voxel segmentation, also VV segmentation. And so, for example, in my CT images, I was able to look at these very dark voxels, which I classified as a log-like component. So it's the background, fractures, also organic matter. And I was also able to decipher and distinguish matrix, which is the main mineralogy, main component, carbonates, which I was able to observe it on a preliminary analysis of infrared, and also opaques, which are mainly oxides and sulfides, and which appear here very bright. And some of the lag values I couldn't attribute a specific component, so I classify them as mixing. And so this results in a stack of component maps in which we can already start to observe some mineral assemblages. However, this method is user-dependent because we have to choose the thresholds for the lag values, but we also have a prior knowledge of our sample, either composition or components. And we also need here to do a manual contouring for detecting the mineral assemblages. And so here I will explain you the new method that I have developed that was part of the recent paper that was published on the MAPS journal. And these methods try to overcome all these previous issues. And so here, we are not looking at one voxel, but a group of voxels. And because we saw that depending on the lag values, we can have different components, looking at one macro voxel, we can have information of a mineral assemblage. And this mineral assemblage, or this macro voxel, can be seen or analyzed through a histograms in which we can have access to the number of voxels for each given lag values. So for example, if I have a macro voxel that contains a lot of carbonate, I will have a lot of voxels rich in the lag values corresponding to carbonates. If I have a matrix rich with fractures macrovoxels, then I will have a lot of low lag values voxels. So the histogram will be shifted on the left. And on the opposite, if I have a macrovoxel with a lot of opaques, then the histogram will be shifted on the right. And so this technique, this technique is sensitive to the mineralogy and also the physical properties of the lithology, such as grain size or fractures. However, now the question is, how do we go from CT images to macrovoxels? And so the first step is to generate local histograms, so generate mineral assemblages. So the first step that the user has to do is to select a macrovoxel size, which depends on its sample, but also on the heterogeneities that the user is seeking. And for me, because I was looking at heterogeneities about tens to hundreds of micron, I choose a macrovoxel size of 25 voxels, which correspond to approximately a cube of 33 micron. And so then we have our set of CT slice that is transformed of a set of macro slice with a given number of macrovoxels. And for A0159, it results in thousands and thousands histograms. So now the question is, how do we go from these multiple histograms to mineral assemblages? So the second step is to extract these typical histograms and extract typical assemblages. And to do so, I first separate and splitted the histograms coming from the background and histograms coming from the samples. And then I performed different user-independent mathematical algorithm to extract the typical histograms of my sample. So each result, A0159, can be described by 12 representative histograms plus the background. And if we can use these histograms to segment each of the macro slices that we have in the samples. However, here, for better 3D visualization, 3D interpretation, and 3D and then discussions, I have performed the further step and I have grouped histograms together thanks to their peak parameters and spatial correlations. So now A0159 can be described by 5 distinct lithologies as seen in this macro slice example. So before going really into the local histogram results, I wanted to show you a very specificity of A0159, which is its abundance in carbonates. And here, which can be allowed by the voxel by voxel segmentation results. So here what you have the carbonate components in yellow, in the grain, which is in gray here. So our sample is very abundant in carbonates with a carbonate to matrix ratio of about 0.5. We can see some individual carbonates that are splitting around the sample, but also these beautiful vein structures that can reach the millimeter on the vertical axis. And this is the first detection of such and 3D visualization of such a carbonate vein in samples such as Ryugu or even CI chondrites. So now these are the results of the local histogram segmentation. This video shows the distribution of the lithologies in A0159, and here is just the 3D model. And because we have access to lithologies everywhere in the sample, we know that we can estimate their proportion. And here we have lithology 2 and 3, which are the main lithology in A0159. So this method provides a comprehensive study of the formation of the lithologies in the sample. On the left, so now we can go inside the sample. And here you have the macro slice, which contain this slice. And here you have the voxel by voxel segmentation result. And what we see through this local histogram segmentation is that the lithology are better defined. So we are able, because we can interpret this, because we are human and so we can subjectively interpret these results, we can see that there is this well-defined mineral assemblages. However, we observe also some more subtle lithologies, such as the purple ones, that it wasn't that clear that it was a specific mineral assemblage. And here we can also, through this method, we can also observe the specific relation between the different lithologies. For example, we have the lithology 4 here that is mainly corresponding to the carbonate vein that is inside the lithology 2 and which itself is surrounded by the lithology 3. So now that we have a bit of context of where are the lithologies distributed in the samples, we can now perform 2D surfaces. So I choose 3 2D surfaces to sample these lithologies, such as shown in this plot, in this figure, sorry. So the main section is the cut one, so I will call it after Pangea because of its shape resemblance with the continent. Here you have a backscattered electron image, and this is the larger sections, which is millimeters wide long. And I also performed 2 other smaller cuts, cut 2 and cut 3. And so in the following, I will be mainly focusing on Pangea and cut 2. And just for you to have a marker, we will have now this carbonate vein that is horizontally located on Pangea section. So here you have the results of the Pangea and cut 2, and also how are the lithologies located in the samples. So you have the vein here, and you have mainly the lithology 2, and also a bit of lithology 3 here, and cut 2, which is mainly composed of lithology 1. And so because of these results, I was able here to select 5 regions of interest and representative tiles that are shown here. And here you have the color composition of these representative tiles of each lithologies. And what we see is that we have this lithology 4 lithologies that is mainly composed of carbonates present in or shown in red. It is 57% of the total mineralogy. And as you can see on this color composition, red is present everywhere, which means that carbonate is present almost in every lithologies. But instead, they are present in a lesser amount. And instead, these lithologies are enriched in matrix, reaching 94% of the lithology 1. In lithology 3, these elemental compositions allowed us also to observe small, so it appears in magenta here, and there are small phosphates. And also in lithology 3, we were able to observe some phosphides. So here the conclusion is that all lithologies are quite similar in mineralogy, however, they are still distinct. And all the mineralogy is from aqueous alteration. So now I will focus on the matrix heterogeneities and the matrix components in the sample. And especially I will focus on lithology 2 and lithology 3. So on the right here, you have an intensity ratio map which shows the abundance of sulfur. And what we observe here is that there is this dichotomy and this limit between lithology 2 on the left and lithology 3, which is in blue, on the right, which appear more yellow. So it means that lithology 3 is enriched in sulfur. What we observe also after this limit is that this carbonate vein is cross-cutting these boundaries, which in terms of geology principles, the carbonate vein happened after the limits of lithology 2 and lithology 3. And what we observe also on this map is that there are some smaller scale heterogeneities, which are also visible using the magnesium map here. So here the heterogeneities are either depleted in magnesium or very enriched. And if we look closer at these heterogeneities, so here you have the magnesium to silicon ratios and the sulfur proportion, we observe this tendency with 3 points enriched, more rich in magnesium, but also very depleted in sulfur. And these correspond to the coarse-grained phyllosilicates, which are mainly pure phyllosilicates with almost no other minerals. And on the opposite, you have 5 points that correspond to these very specific heterogeneities, and they correspond to fine-grained phyllosilicates with numerous nanosulfide and smaller sulfides. And the rest of the points are fine-grained phyllosilicates with a lesser amount of sulfur. On this map, again, if you look at the magnesium elemental ratio, we observe that there is no specific difference between lithology 2 and lithology 3. However, we can observe a small limit here that is shifted on the right. And here, so we keep focusing on the matrix heterogeneities. However, we are switching to infrared spectroscopy results. So what we observe here is an RGB composition. So it's made of 3 parameters that is focusing on the silicon to oxygen stretching bands, which is typical from phyllosilicates. So the red components correspond to the positions of the peak maximums that is around this wave number. The green components correspond to the intensity of the spectrum at this wave number 935. And the blue components is the positions of the first derivative. So at the positions when the slope steepness changes. And so here you have a spectrum that corresponds to the lithology 2. And what we see if we go from lithology 2 towards lithology 3, that we observe that there is an increase of this intensity and also a change here. So here on this map, we observe both sulfur and magnesium limits, but also kind of a progressive transitions from lithology 2 to lithology 3. And this map also allows us to observe and to detect new regions that is in dark blue here. And these regions also have a specific spectra, which is very depleted at the wave number 935. And if we look closer at another part of the spectra, which is the OH stretching bands, which correspond to the hydrations of the phyllosilicates, what we observe is that the three first spectra has this typical band that from phyllosilicates. However, the new spectra also show a depletion at this band, or even maybe it is absent or depleted. And so these depletions can be characterized by the OH loss and OH group loss that can be due to a heating process. And if we look closer at this new regions matrix, we observe these round vesicular features that can be attributed to vesicles. And vesicles are very typical from phyllosilicates after their dehydratations and by dehydroxylation, so the loss of OH group. And this happened at a temperature from 4 to 500 degrees, so over 4 to 500 degrees. So these textures supports also the heating event of A0159 or these specific regions. And the heterogeneity in the phyllosilicates, here you have the carbonate results. So the carbonates are all depending of the lithologies. However, we did observe standing of the lithologies. However, we did observe some chemical zoning of the carbonates, with the inside of the carbonates being depleted in magnesium, and an increase of magnesium going to the rim of the carbonate vein, and also individual carbonates. And in A0159, I also observed a lot of fractures. As you can see here, they are all highlighted in white. And what we see is that there's this dichotomy between lithology 2, which is enriched in fractures, compared to lithology 3, that is less rich in fractures. And especially, we observed a lot of fractures around the vein, either parallel to the vein edge, but also a lot of perpendicular to the vein edges fractures. So now altogether, these results allowed me to discuss the formation of these lithologies. So what we saw is that there is this carbonate vein that is crossing the sample, and that all lithologies are dominated by aqueous alteration mineralogies. So what it means is that the formation of lithologies needs a fluid, which is so the fluid is required, which means that because the liquid fluid is not stable on Ryugu, it means that all the lithologies were formed on the parent body. So now the question is, are all lithologies formed during one single aqueous alteration event? And here we observe that the dolomite and the vein is cross-cutting the limit between lithology 2 and lithology 3, and also that the dolomite is present in every lithologies. So I suggest here, so due to the geology principles, that the carbonate precipitations formed after the formation of lithology 2 and lithology 3. And this suggestion might also explain the opposite tendency with other works that observe the opposite tendency in the chemical zoning of carbonate. So now we can focus on lithology 2 and lithology 3. And so how are these two lithologies formed? And here I will go through three hypotheses: the brecciation process, the alteration front, and an initial heterogeneities in the accretion. So the brecciation process is the mechanical rocks mixing of different of fragments coming from different locations in the parent body. And so it has been proposed, for example, in Orgueil samples through the work of Morlock et al. However, in our sample, the mineralogical differences between lithology 2 and lithology 3 are very subtle. And the limits between the two lithologies are not as sharp, and it seems that there is a progressive transition. So now, the hypothesis of the alteration front. So it has been proposed by Connolly et al. from the Bennu samples, which is a second return sample missions. And here they propose that an alteration front arrived and enriched the phyllosilicates in sulfurs, which creates these very specific and distinct lithologies. So it means that this part is more altered than the part on the right. And if we apply this hypothesis on A0159, this would mean that the lithology 3 here would be the more altered. However, we observed some particular minerals which might be attributed to more primitive materials. And so here I will finish with this third hypothesis, the local heterogeneities during an accretion process. And what I propose here is that there is this different local ice-to-rock ratios or various proportion of primitive materials. And this could, after the alteration fronts, this could explain the subtle mineralogical differences between lithology 2 and lithology 3, which is also consistent with the distributions and the distributions of lithology 3 that is surrounding lithology 2. So here, because they have subtle mineralogical differences, I suggest that the initial lithology 2 and lithology 3 was due to an initial heterogeneity during the accretion. However, the question now is also, does A0159 record any more physical processes that occurred after this formation of its lithologies? And here we observed the perpendicular and parallel fractures that is really similar to the experiment of Noiriel et al., in which they produce and they precipitate halite in a porous medium, and due to the precipitation pressure, some fractures appeared and created in the volume, even with the porous medium. So here I propose that the carbonate vein produce fractures due to its precipitations. And of course, we also observed some vesicles that were imprinted in the matrix, which suggests that A0159 suffered one or many impact events. So here's the final scenario for placing A0159 in the general context of its parent body. So here you have the beginning of the solar formation, and here we are now. And so, as thought, the parent body of Ryugu would be formed in a mixture of ice and anhydrous dust beyond Jupiter's orbits. But here I propose that they were formed through an initial heterogeneities, either the ice-to-rock ratio that can change or some primitive mineral proportion. Then, with the radioactive decay of aluminium-26, the aqueous alterations happened, and then the heterogeneity would be conserved through this alteration, but creating some progressive change in the lithologies. And then at this time, because the heating can also not be homogeneous in the sample alteration, so not only one event, and especially here I propose that such a multiple aqueous alterations event could have been formed also by the smaller scale impacts that could have released some fluid after their crystallization in ice and remobilized some fluids, which led to the formation of this carbonate vein. Also, impacts can create heat, also displacement. And then this carbonate vein would have been precipitated and then creates fractures. And this is also something that was proposed by Iizuka et al. Recently. And then the parent body of Ryugu would have been disrupted through impacts, forming the Polania-Eulalia family, forming then Ryugu, and then Ryugu became a near-Earth asteroid, and A0159 was sampled after by Hayabusa 2 space mission on the Ryugu asteroid. So when I first received grain A0159, I didn't know anything about it, except maybe its size or also some primary spectra. And now I'm able to say that A0159 is composed of 5 distinct lithologies that are all specifically distributed in 3D, and also that there is this millimeter-sized carbonate vein in this sample. And this was able due to the, as a result of this new local histogram segmentation process that have developed called the local histogram method. And this enables the analysis of lithologies without any distractions, which is user-independent, semi-automatic, and also non-destructive nor invasive. And then, thanks to this method, I was able to choose specific 2D surfaces to perform further analysis to obtain and to better characterize the lithologies. And so altogether, this 2D surfaces allows me to have observe that lithologies are close in mineralogy, but still they have subtle differences, and also that some of them have a progressive transition. And some, in A0159, I observed a lot of fractures around the vein that I suggest to be hydraulic fracturations, and also some morphologies that might be related to a heating event. So altogether, I was able to construct a consistent scenario, placing A0159 in the context of its parent body. And then, to better constrain this scenario, what I suggest is to perform isotopic analysis on the carbonates, but also on the different mineralogy in the lithologies to better understand how many aqueous alteration events, when, and what were the sources. And so to go further on the LH segmentation, now that we have applied this these methods on A0159, we want to apply it on multiple samples. And this is, we did already some first tests, and we showed some very promising early results. As you can see here, we can see some homogeneous grains, some heterogeneous grains, some lithologies that are located in different grains. And so I already faced some difficulties, but I already have some improvement in progress. And however, this first application of these methods on 6 grains of Ryugu's offers the first user-independent, comparative, and representative analysis of lithologies in extraterrestrial samples. And for further application of this method, of course, we could apply it on the pressure and rare samples from return sample mission, such as Ryugu, Bennu, also the Moon or Phobos. And because the local histogram segmentation method is able to detect heterogeneities, it could also be applied in other fields, such as in geology or archaeological samples. So thank you very much for your attention. And I will leave you here with these slides, which correspond to what I have done also during my PhD. Thank you very much. Je les ai briefés avant. So before going to
before going to the question, we need to switch the mic so that you can hear people on Zoom with the...
Okay.
And people, if they want to leave for the question.
Je coupe mon micro. Il faut que tu mettes le tien sur la boîte.
OK. Et j'allume mon micro, moi, du coup.
Là, normalement,
Ouais, Romy et Frédéric, normalement, vous devez nous entendre. Et si vous parlez, on devrait vous entendre aussi. And, sorry, Romy and Frédéric, if you can hear us normally, and we are normally able to hear you. Can you try to speak, please?
Can you hear me? Hello?
Yes, so yes, we hear you. I will just put the sound. Yes. I think we hear you well.
Okay.
Can you please say something?
Hello, ça va? Vous m'entendez bien?
Oui, oui, ça va.
Ouais.
C'est bon. Bah, je laisse la présidente me lancer, mais bon, je suis prêt.
J'essaye là.
Oui, vous m'entendez toujours?
Un peu de loin, mais pas le plus proche.
Comment je...
Si tu peux mettre au milieu.
Ouais.
Pas au moins pour...
Non, pas trop. Maybe if you go closer to your laptop.
Yeah. Can you hear me well now?
Now
Yes.
it's better.
Okay, I will speak
So,
very
Léna,
loud.
thank you so much for your presentation. That was indeed very clear. So now it's time for questions.
Yes.
And so I give the floor to Frédéric Monnier, who is a rapporteur.
Okay.
Frédéric, à toi.
Thank you, Sonia. Thank you. Okay, so I will start by saying a few words, Léna. So first, thank you for inviting me to participate to this committee. It was as I will repeat a few words from my report. It was I really appreciated your thesis. I'm a bit outside of the techniques that you are using. I was a bit afraid actually when Rosario asked me to be a reviewer on this, but the manuscript was very clear. And today you gave a very nice presentation. The presentation was probably even nicer than the manuscript. You did pose the scientific questions very well, and so I will congratulate you for both the thesis again and for the presentation today. Of course, I have several questions. I'm here for that. And also, I apologize that I'm not here with you today for some little back problems. I wish I would be here.
I hope you will be better soon.
Oh, so thank you. I will be nice now, so if you say that. Okay, so first, I'm amazed also what you can do with such a small sample. You know, I worked a lot on this. I mean, I worked on these samples on Ryugu and other samples, and my approach is always with big samples, lots of material. So it's all the things you can say from such a small sample is honestly is quite it's great, especially with your new approach. But my first question is of course connected to the representativity of such a small sample. My experience with Ryugu, with the chemistry of Ryugu samples, with the bulk chemical composition, is that what us and other people observed is heterogeneity even on a large scale, you know, on tens of milligrams of materials. So maybe my first question will be first, how do you kind of discuss that a little bit already, but how representative you think all your story is compared to what we already know at a larger scale? And I will go really ask you two questions here, and then you can discuss. Is that the other one will be an advice from you in some sort? I am part of this, Ryugu reference project. So now we want to take 1 gram of Ryugu or less if we can to try to really get what is the composition of Ryugu. And so from your experience now on A0159. What kind of sample size and statistics we will need, you know, to try to answer this question of what is, if it's even possible, what is the bulk scale mineralogy and composition of Ryugu?
That's a very good question because so far all the samples analyzed were still homogeneous, but at the larger scale was in an elemental composition. It appears to be homogeneous. So at the smaller scale, they are heterogeneous, but on the larger scale, they appeared homogeneous. And so here I well, it's a kind of luck also, because I really obtain a sample that is very, very specific. And so it is not representative of what we observed in other samples of Ryugu. So we need as a very lot of it's hard to say how do you say a mass or something like that, because as you can see here we had, so it's 3.4 micrograms, and it's a sample that is very different from the rest of the other samples. So maybe if we want to have something that is representative, maybe we first have to look on the samples and observe if there are some more specific or specific samples, and in that case maybe the specific samples are kind of exceptional, and so maybe they shouldn't be taken into account in this larger scale analysis.
Yes, exactly. So, but you say something, so sorry, maybe I missed that. Why do you say your sample is so exceptional? So did you compare that to, I mean, what is your comparison here when you say it's a very exceptional sample?
I'm comparing with other study of Ryugu samples, and mainly on the analyses that were performed on 2D. So maybe also some interesting things are hidden by this technique. But here, what is very specific is this millimeter-sized vein. So the grain of A0159 is very enriched by like 16 times compared to Yokohama et al., for example. So the calcium is very important in this grain. So it is not like the previous analysis.
Previous grains. But I said actually even the calcium at the bulk scale is very variable. You know, in a large powder, the calcium content of Ryugu samples is very variable. So even on a large scale, it's not homogeneous actually. But even if we try to homogenize, we homogenize two samples of about 40 milligrams. And other groups did that also, like Eizo Nakamura. And it was actually by, you know, like the range is almost a factor maybe 4 or 5, I forgot now, but of calcium content at the bulk scale. So what you see in your vein, probably, I mean, it's very interesting, and it's, I don't have the answer, right? But this is something we're trying to think of, but how to select, you know, the samples. But how did you choose A0159? Is it what you got sent by JAXA, or there was some specific, how to say that, criteria this sample to start your study?
So it was first by its size. So we wanted larger samples to observe, to have a greater chance to observe lithologies, but also we had constraints from the XCT setting, so it couldn't be larger than 3 or 4 millimeters. And as you know, there are not a lot of large samples, so we couldn't ask for 20 millimeters because they don't exist. But so yeah, the size first, and also we had already an analysis of the infrared spectrum, and from Le Piver et al. 2023, I think now it's published. 2023, and in which A0159 appears on one of the opposite tendency. And so it was one of the chance to observe maybe also less or like in the extreme of this plot that was showing the alteration of different degree of alteration. So we wanted to choose one of the opposite tendency.
Okay, so there was some good consideration before you selected this sample.
Yeah, but mainly was the size also.
Okay, thank you very much. Okay, I just thought about something during your talk, and it's not if you don't have the answer, it's not a tricky question, but Do you know that during when the parachute of Hayabusa opened, the capsule of the samples did open a little bit, and you had some air which went inside the capsule. So you yes. So we always say, I should not say that, but we always say that the samples are very preserved. They are, but there is a little bit of air that came inside, something like 70 Pascal, or so factor 1,000 compared to the atmospheric pressure. So because you see all this oxidized phase. Okay, you didn't know about it, but it's fine. But do you think that this could have an effect on the small? Again, I don't have the answer because I never look at such small phases. But do you think at this small scale this could have an effect if you had some little bit of oxygen to your samples for a very short time? But
so during so after the fall, some air came
when
in.
the parachute opened, so it
Okay, and then that could oxidize some of the grain inside.
No, maybe.
I don't know the time of the oxidation, but I think it might have impact of create sulfates and stuff for the oxidations. I have no idea, but I mean there is always a risk if the oxygen enters, but maybe also. So I mean in the surface of the grain, but if we look at the inside, maybe the inside is still pristine.
Yeah, probably you're right. And just I think you mentioned that at the end. So
Frédéric, please, may you speak closer to the microphone?
Sorry. And for the carbonates, I mean the answer you gave it already, but how do we know all this alteration is from the parent body? How would you test that? Actually, okay, you mentioned because it was dated, right? And can you? This I also don't know. At the small scale that you see your carbonates, is there a way to date this alteration? The aqueous alteration. Can you hear me?
Yes. Well, I would love to do isotopical composition on different carbonates of the sample, so the vein, but also individual carbonates, maybe very far away from the carbonate vein, sorry. And I actually don't know how large the size of the carbonates has to be to analyze to obtain isotopical analysis. If it's the same as secondary mass spectroscopy. Oh yeah, spectrometry.
You can say ion
maybe
probe.
Ion probe, yes. Maybe only a few micron is needed, or even smaller.
Yeah, I mean, because I think here you have a very nice, what you developed is for this would be a very nice way to select, you know, the future 2D sections to do this kind of measurements. So this will be here you have many things. I think you will be able to further test and select all your lithologies and to go next. And it's what you put in your conclusion. To go a step further there will be to select the sample this way.
Yes.
Okay, I have another question. It's always the same idea, but with these techniques that you developed, many of the papers that you see now on Benu or Ryugu, people focus on the organic matter. And this is not something that you have presented here. And I'm not a specialist of organic matter, but this is something that I was wondering. So there is many papers on soluble and insoluble organic matter. And I was wondering also with your approach, of course, you cannot detect organic matter, but is there a way to select here maybe some zones which will be enriched in organic matter and to study their distribution, or this is totally out of reach with what you are doing?
So indeed, with the XCT technique, we are not very able to observe patches of organic matter because organic matter is quite transparent to the X-ray, so it appears dark. But also, if we had a larger, like a very large patch of organic matter, we might see it. However, now the organic matter that we found are sometimes we observe the sulfide inside, and so it's very hard to detect the organic matter through XCT. However, we also had the chance on the slice, and we observed some patches of organic matter. And there is actually a collaboration with other laboratory that observed this organic matter. And if I'm not saying it wrong so far, so just to explain, the patches are quite big and squared. And sorry, I forgot to put that on the backup slide, but I put it on the manuscript. There are like 20 micron sized squared of organic matter. And so it was quite specific, but the analysis so far doesn't show any difference compared to other previous studies. So to answer, it's sure that it's quite hard for us to go to select to observe organic matter through XCT, but if we are lucky, through the 2D surfaces, we can analyze it. And what would be nice also, maybe, is to analyze the organic matter from one lithology compared to another one, to see if there is changes.
And so how would you select the lithologies? Which one?
Micro manipulation. No, yeah, that's a good question, because usually the techniques, so you need a piece of the sample that you have after to destroy and do a multiple extraction. So it would mean that we have to split the lithologies or to select, and I think we need a quite high mass. So yeah, I don't have this answer.
Good. Okay, so if I go to your discussion.
Yes.
And you have this this very interesting proposition of this variable water rock, water minerals, this heterogeneity of the abundance, the ratio of water and your minerals. And can you go back? Maybe this is one of the conclusion slide, right, where you have your scenarios. And it's a very nice slide. I think it's this one. Yes. Yeah. Is it this one? No.
This one?
No, before. Sorry, when you show the 3 scenarios that is possible. If you go back a little bit.
Like this one, maybe the 3 hypotheses.
Yeah, exactly. So this initial local heterogeneities, which is your favorite explanation, right?
Okay. Sorry.
Yeah. How do you really envision that?
Yes.
No, go back to. Sorry, can you just go back to where you were just before? Here. So the initial local heterogeneity. So it's at a very small scale, right? So the idea is that at a very small scale, you have a mix of ice and minerals, if I understand well, right?
Yes.
This is that, right?
Yes.
Okay. So this is really at the scale. So you have some minerals have a lot of water next to them, and some other minerals have very few water, right? And
yes.
So, I have.
Oh.
How do you envision that? Why would that be heterogeneous in this water abundance? What would be the reason for it, I should say?
Yeah, I it's a good question. Because for me, it is something that might be happening during the accretion. So because the parent body of Ryugu probably didn't form in a few minutes, maybe the dust that is coming to accrete can be from different location, but still in the same location in the accretion disk. But they might have already suffered more irradiations and less water or dehydratation if because I remember I saw also one hypothesis, or I don't remember what, but something that was hid, like for example, in the accretion disk, if so you have the sun and you have the matter, but if there is some stuff between the sun and the matter, that might be less, for example, irradiate, and so maybe less, they might keep more water, or like I imagine like small scale heterogeneities, but they are not very big. Like for example, the literacy 2 and literacy 3, they are quite similar in mineralogy. So I don't know. I think it's something that has to be a bit to dig. It's something to dig.
It has a small scale. So again, I never really think at this smaller scale. So it's because this is, we had this paper came out that I think it's nice because you cited it there. It is Izuka, in which based on some lutetium, some isotopic work, proposed that you had this much more recent aqueous alteration, right? With a different source of heat. So it means you still had ice, and one of the conclusions of this paper is that actually this CI chondrites, whatever, parent bodies kept ice for a long time. I mean, more recently.
Yeah.
So one important implication here, and I was going to ask you that with your scenario of this heterogeneous abundance of water within the parent body. So do you have any idea of what this will influence our estimation of the water content of the parent body? Because there is some water rock ratios, between, I forgot, 20 and 60 times, I think, something like that. But if it is like this, this heterogeneous distribution, will that have any effect on this abundance? And because it has important consequence to the origin of the water on Earth or on terrestrial planets.
So the question, sorry if I'm not sure.
No, the question, because it was not very clear. It's my fault.
Okay.
I was saying that this heterogeneous, with your scenario of this heterogeneous distribution at a very small scale, right, of the water, can this have any influence on our estimate of the total water content of the parent body?
Well, I think it brings to the first questions, like at which scale do we have to look for having a representative estimation of either elemental but also water rock ratio. So if you look at, like, for example, the water rock ratio that would form the less altered is very low, but most of the Ryugu samples are very enriched in mineralogy. So it means that there is a certain amount of water. So I think we still have to look at the larger scales also. And maybe, and I think maybe the heterogeneity or the water rock to rock ratio, or the heterogeneities in the samples, they might stay quite local too, not like a fluid, like a tsunami that goes within the parent body. So
I don't know. I think with a small scale, and again, I think this is very important because this is something that we misregard very often. Okay, do we have a bit more time, or I'm asking the president?
A very last question, Frédéric, please.
Okay. Actually, I will finish with something on the future. There is all this. I think you answered that also in your conclusion, so it will be an easy one. But you have all these future sample return missions. Okay, one thing you didn't. Okay, no, sorry, I will change. I will. I'm sure someone else.
Not this question.
I changed my question. I have another idea. There is this debate now about the connection between Bennu and Ryugu, and with all the new data on Bennu and there is at least some debate on, is it coming from the same group of asteroid and the same, you mentioned, you know, Polona or whatever. With your method, with your data, actually, what you do on scale, and if we give you samples from Bennu, what would you do to test this? Is there a way you can do to test this with this small scale approach?
Well, that could be interesting to. So as I showed here in this, we might we could compare different samples. So for example, like here we have 6 samples from Ryugu, but we could also do 3 samples of Ryugu and 3 samples of Bennu and to compare what is the result of this local histogram segmentation. And if we see and if we observe some common lithologies, and so that might help us to place Bennu and Ryugu in the larger scale of are they coming from the same parent body? And we might be also more lucky to find carbonate veins, because there is one paper that will come soon also, that in which they observed a carbonate vein in Bennu. So maybe Bennu has more carbonate vein than Ryugu. So that is also kind of making maybe the link or the bridge between Bennu and Ryugu.
Okay. Well, thank you very much.
Thank you.
I'm done.
Thank you, Frédéric. Now the floor is to Taha.
Thank you. Well, first of all, so I will start like Frédéric, because when I received the invitation to be on this committee, I thought, well, I am a geologist. What am I doing here? But I read it, I found it.
I'm a geologist too.
Yeah, so what are you doing here?
Geologist. Good question.
But well, first of all, I would really like to congratulate you. This is a really impressive work. You have combined many methods which are difficult, and I know some of them, not all of them. And I know how frustrating it can be going to the cyclotron, for example. But sometimes you don't. When you leave the beam time, you have no results, so you are very lucky. Very good. And also, the thesis was nicely written. It was very pleasant to read. And so this is what I wrote in my report. So really, thank you. So thank you. I thank your supervisors to have invited me, and I thank you for this work. So, but I mean, I'm also here to ask some questions and to raise some points. So I will first start with things that I wrote in my report, and then I have some other points that I thought about during the discussion. I will start with actually a question about the last chapter, when you added new grains. Then when I read it, I had the impression that it changed everything. So what can we
We lost you.
C'est bon?
Ah, c'est revenu, ouais. Il y a eu, ça a frisé.
So you made this correlation between the values of those absorption coefficients and mineralogy, and then you add those new samples, so those new grains, and then it doesn't fit. So how can what can we do with that? So that's my first question.
Yeah. So, well, it's so the local histogram segmentation was performed on 6 grains, as you can see here, and we faced of the lithology detections. For example, we observed that this vein is here in cyan, in blue, but also it appears blue some other in other part of the grain. So I think here what happened is that through the selection of representative histograms, because we are using clusters, it takes the large amount of histograms. And so I think some histograms, so for example, histograms from the carbonate vein is quite similar to other histograms that are located in a bigger amount in other grains, so such as those ones. And so I think the carbonate vein is quite lost because it's very specific, but it doesn't represent a large amount of the grain. So I think we have these difficulties to face. And what I propose here to overpass these difficulties is to do a work like a larger one and then go into details into specific grains. So like the first step would be to have a first big characterizations on a larger scale and then observe some specific grains. And I want here to make you notice that A0159 is still specific here because what is coming out here is the this lithologies that is found only on A0159. And what I think here is that this lithology is detected because there is this large amount of fractures, which might result from the vein, or which I propose results from the vein. And so the larger scale analysis would let us to select specific sample, such as this one and also this one. And then if we go closer, we and then perform the local and more local histogram segmentation on this grain, and then we would be able to find this carbonate vein, etc.
So it's not a matter of the size of your macro voxels?
No.
Okay.
The size of the macro voxel will impact, like you could, like for the size of the macro voxel, if it's too big, you will miss the mineralogical assemblages. But if it's too small, then you don't have histogram, so you cannot very compare. But for me, it's so no, it doesn't affect the sensitivity.
Okay.
It's more a matter of how much histograms I have in my data sets.
Okay. So about making the relation between the absorption coefficients and the chemical composition. So I made this suggestion, but maybe it's really stupid. So don't hesitate if it's stupid. I mean, I'm here also to be observed. So, but is it possible? So you worked at 25 kV. Is it possible to work around the absorption age of some specific element, and then just to map one element like iron, for example? And are there like limitations? Is it possible? Is it something that you have considered?
It is something that it is usually that we can do also. So it's called the dual beam energy XCT or something like this.
Because you can subtract.
Yes, and so you place one energy below the kH of the iron and one energy at the higher of the iron. But as you wrote in your manuscript, we would be able to.
It's my report. It's not my manuscript. This is your manuscript.
In your report, is that so? For example, iron, it's possible. However, not with Psyche, for example, because they start at 17 keV, further like to 150 keV. So it's technically not possible on Psyche. But some other studies have done it. But here, once again, we won't be able to find the mineral assemblages. We would be able to better characterize the iron in the sample.
Yeah. Okay. Yeah, because
but it works.
Because calcium is just too low energy.
And too low also. Calcium, magnesium, it's too low, it won't cross, and especially because we are looking at a millimeter size sample, so it's
Something about calcium, something I did not really notice, but when you show you show some SEM images of the vein, and I did not really notice that there are sulfides which have euhedral shapes.
Within the carbonate vein?
Yeah. You have like,
maybe
there
here?
is one slide.
Like
Yeah,
here?
yeah, you have another one. You have slide 23 maybe. The next year.
Ah, here.
Yeah.
Ah, yeah,
Yeah.
here.
So why?
Why?
I mean, you know, I come from Clermont-Ferrand, so we
Yes.
study volcanic rocks. So
Yes.
this really looks like microlights in in lava. You see, so I know it's
So the
carbonate.
carbonate is the bar, right?
Yeah.
So like in geology, it means that it's coming from the external chamber. Now, if I
No, but I mean like this, the shape,
the shape.
the growth shape of
Okay.
those crystals, and also on the second one, we also have like a sort of euhedral crystal.
So
Maybe it's a carbonate, you think?
these
Crossed my
pyrotites,
mind, yes.
this pyrotite, because they are very well shaped, it means that the thermodynamical condition is very stable, and
Yeah.
that the
Yeah, totally equilibrium, yes.
the mineralogy has the crystal has the time to grow and to form well-shaped crystals.
Maybe
but-
it says something about timing, yes.
Mm.
Yeah.
Yes, and I think like compared to the carbonate veins, which is it's a lot of minerals. So I didn't show it here, but the carbonate is not one unique mineral. It's smaller scaled minerals that is all stuck together, and we don't have like well-shaped crystals so far from the carbonate. So it means like it appears that the carbonate vein is not wasn't growing at an equilibrium, like less at the equilibrium that the pyrotites, so the sulfides that are very well defined.
Okay. You said something during your presentation about losing OH due to heating, and then, but it seemed to be very small scale contrast. So how can you imagine having a difference in temperature at 100 micron scale in terms of process?
Like for example, if
You had the scale, yeah, here,
Yeah.
yes, yeah.
So
So the
for
scale bar,
example,
yeah.
what I think, what I say here is that this would be more heating than this
Yeah,
this
but
area
yeah,
here.
but the scale bar is 300 microns,
Yes.
so in terms of thermal diffusion, it's not
Yeah.
that
I don't,
large. So
I don't know. It's because it can also depend of the temperatures, but also the duration of the temperatures. And so I don't know how, like if there is something that is heating somewhere here, like how long would it take to dehydrate this area, but not the other part of the sample? That's a good question. I think.
yeah, I didn't think about
So-
it before you showed.
And like what something else, like maybe it's another processes, another heating from this region.
Is it something with a sample preparation, for example, with the ion beam? Is it possible?
Maybe from the plasma
Yeah.
focus ion beam. Yeah, actually, this is something that that was also thought. However, it would mean that these regions would be more fragile or specific,
Possible.
because the rest is, we do not observe that. So yeah, maybe it, but so it means that there is something in these regions that would lead to the matrix to be more fragile. To however, I don't think these areas, I don't know actually, but this I don't know if we can reach this point, like because we are able here to see vesiculation on the oxide. So
But it's not the same size.
no, it's not the
Yeah,
same
those are
size.
larger.
Yeah, it's smaller. Yeah. So maybe it can be a result of the plasma feed focus ion beam. Yeah.
And
But I don't have the reason of why this region would have been.
you need it.
Détection.
Talking about temperature, this is something I wrote in my report. So
Yes.
you said that there is organic matter,
Yes.
and is it possible to do use Raman to evaluate, to determine the temperature? You know, Olivier Bessac and other
Yeah.
people at the museum
Right.
use that. I don't know at the IMPMC.
I saw that there is, like, depending on the temperature, you will not have the same organic matter, or it will change through the, like, increasing the temperatures. So yeah, maybe that could be a good way to better constrain these temperatures. The two larger patches that I was talking about, which are very big, they are located somewhere here.
Mm-hmm.
And here, they are not like big patches, but maybe we could still find some.
Yeah, just to confirm your
Yeah, that's true.
what you said. Yeah, now I have one. It's more like a technical question about your when you presented those X-ray maps. So I'm sorry to use that phrasing, but you claim a resolution which is below 1 micrometer per pixel. Given that you work at 15 keV acceleration voltage, I don't think this is. I think you are too optimistic.
Yeah.
So.
But like, for example, for those points,
for
these ones.
Yeah, no. Well, this is well. I have another comment, but I mean, we can talk about it later. No, but just when you presented those X-ray maps, and at some point you have a discussion about the spatial resolution, so the size of the objects actually that you see, and I think that at 15 keV, it's the spatial resolution it cannot be better than 1 micron.
Yeah, it's because of the
Because you're working on thick sections. If you had a really thin section, maybe, but I don't think that this is on very thin sections. So
no,
actually, I checked.
It's large section.
Yeah. So perhaps there is a little. Just be careful here on this.
So the size of the micron, the size of the pixel is this.
Yeah.
It's this resolution, but instead the composition, like the composition itself, samples more than one pixel. So that's why also I select regions of pixels to have a larger representative analysis.
That's fair enough. One thing. You said that you have phosphides and phosphates.
Yes.
I think it's very interesting.
Yes.
But because here you have an oxygen fugacity, you have the possibility to calculate the oxygen fugacity of the sample because of the two redox state, so phosphorus. Have you thought about it?
Well, we do not plan to do it, but we didn't plan to do it. But I think it might be interesting to.
But at the same time, you also have oxides, so maybe you have mixtures of things that are not equilibrated.
Yeah, and maybe they didn't also appear at the same time. So I don't know if we can decipher between the different events.
But yes, I like phosphides. And one last thing, and this came up during the discussion with Frédéric, and it reminded me one of your first slides. You showed how you don't need to show, but you had this animation with how this object formed, like first beyond Jupiter, and then when you do the main asteroid belt, and then so this object experienced many events. So we want to understand how they form, and we want to use this as a way to understand the history of the solar system. But because of those many events, how close can we be to the truth if this exists?
I and as we see also, like each parent body has kind of its specificity. Each asteroid has his own specificity. So I think the best is to look at the more or less altered lithologies to observe. Like if we want to have information on the primitive matter, it's better to observe the least altered lithologies. And I think, well, I think what we need is also a larger and global view and how are the planetary bodies formed in the solar system. However, we still have to keep in mind that every parent body might have suffered like different events, and that one big law cannot be applied to each planetary bodies. But yeah, that's why we have to look at the smaller scale, I think.
Yeah, I fully agree with you. I will stop here for the moment, maybe.
One last, if you want.
No, it's good. It's good. Yeah.
Okay, thank you so much. Romy, the floor is up to you.
Thank you. Can you hear me?
Yes.
Excellent. Like the previous reviewers said, thank you for inviting me to be on your committee. And I think I know why I was invited, for the X-ray CT portion mainly, which was very well done. It's excellent presentation. Because I do not speak or write French, I couldn't read your entire dissertation, but I did read the MAPS paper. It was very nice. And I read the summary that you sent of your entire dissertation for the English speakers. Thank you so much for that. And your presentation was very nice. Unfortunately, the previous reviewers took some of my questions, so I've been trying to to like redo what I was gonna ask you. But I think the first one will be, and it seems like maybe you reported this in your final dissertation chapter, but you did look at other Ryugu samples, even though you only reported on the one in the paper. And I was wondering, how did you handle defining the LAC histograms? Did you take the initial definition of the histograms that you found in 159 in 159 and then applied it to the rest of the samples, or did you repeat the process of the clustering and finding the new lithologies for each individual sample?
Yeah. So I did two methods to observe I did apply first the local. Well, I mean, I did during an internship that I have supervised. So thank you, Marius, if you are here. So the idea was first to apply the local histogram segmentation to each sample. So then it results in a specific set of histogram for each given sample. And then I kind of mixed all the XCT data sets from all the different grains, and then I applied the local histogram segmentation. So here you have the results of the histogram, but that correspond to the whole data set of the 6 grains.
Okay. So you did it.
So there's
both
2 ways of doing it.
Mm-hmm.
And yes. And so what we see here, for example, is that we observed already using this analysis, we observed that there is a common lithologies, which are in the middle, and some specific ones. So for example, A0159 that is shifted on the left, and this grain also that is has histograms on the right.
I think you're cutting out. I can't hear you.
I was done. So
oh, sorry. Oh, Well, okay. So you did it first the one way to see how the lithology variation was different between the grains, within the grains. And then can you go to the next slide? And then you...
And this one more to have a comparative analysis of the histograms. So how, like, where are the histograms located and where are the lithologies? But we are talking about the same lithologies here. So, well, I mean, you were comparing different grains and
so how does this work into the heterogeneity and scale of observation issue that the first reviewer that Frederick was talking about? Like, was this informative to tell you, oh, I'm not looking big enough, or does it tell you anything about the scale of heterogeneity?
Well, like, as you can see here again, there is this grain that appears very different. So it's A0159. So for example, if we want to have a comparative and representative analysis, if we want to do like compositional or elemental analysis, we might want to take grains that have similar lithologies. So maybe this grain is better to put it on the side and not observe it, to have a representative analysis of Ryugu. So we could use this local histogram segmentation to select grains that are more common or more specific.
Okay, excellent. Thank you. Okay. Also related to scale, the scale of alteration. So you had the very nice slide about the 3 different scenarios to explain the lithologies. I think a previous person had the other one. Yes, that one. Okay. So you favor local heterogeneities, which on this scale of millimeters implies that, well, it implies to me that the fluid flow and open versus closed system behavior of this piece would be closed system with a very limited fluid flow. Does that make sense? Like, otherwise you would erase all the local heterogeneities. Is that true?
Well, this is something, this is what I'm thinking, but also that they might have fluid at a larger scale or a more open system. If we want to create, for example, this carbonate vein, it has to, we need a fluid flow at some points. But
so
for the heterogeneity here would be more a closed system, and you would alter the mineralogy like locally to keep the heterogeneities, and then through impacts, for example, you have a motion or a movement in which you can also maybe localize fluids through the strength. And then you can also create some more fluid features such as vents or stuff like this. Or as Frédéric was talking about, maybe a fluid flow that erases also some compositional on the larger scale. So maybe we have both of them. More local alteration, and then also some impact related flow.
Excellent answer. Yes, I think this is something that we don't talk about enough. Is just how we can have all of this really local closed system, tiny fluid scale movement, preserving this heterogeneity, and then these evidence for these huge veins on Bennu and Ryugu, but still preserve all the tiny little heterogeneities around. I'm sure, I don't know, it's fascinating, but great. Excellent answer.
I agree.
Let me see if there's anything else that I had left. Okay, so you discussed this in your paper that I read, but how is porosity or other physical characteristics influencing your histograms and their clustering and the identification of the different lithologies? Can you just kind of touch on that again? Your thoughts?
Yes. I think also this part was kind of very hard in my paper, I think, related to the low lag value components. So the lithology 1 here present appears, so I put it here. So lithology 1 is the one that has a histogram shifted on the left. So as you can see here, it has more low lag value voxels. And so this is why we performed more analysis on this lithology. And so the porosity, even if we cannot detect it like directly, like we cannot say like this voxel is a pore because of the resolution, because of something that is very at smaller scale. If a region is very more enriched in pore or more porous, it will shift the histogram on the left. And this is what it taught here for the lithology 1. We think that so it's also multiple different factors because lithology 1 is depleted in carbonate. It's on maybe and it also has a matrix rich, a dark matrix. So what I think here is that it's maybe more rich in coarse grain phyllosilicates. And coarse grain phyllosilicates, so it's only silicates, no sulfides. So everything will be shifting on lower lag values. So it's either microporosity in lithology 1 or also micro fractures, which make the histogram shifting on the left.
Okay, and so do you have any ideas on how you could tease apart whether it was organic matter versus coarse grain phyllosilicates versus pore space using CT?
No. No, because it's very hard to decipher between organic matter and porosity in the XCT. And we had to further analyze like for example, the cut 2, which is enriched in the lithology 1. And we did not observe an enrichment in organic matter. So we conclude that it was a more structural porosity, really. Yeah.
But could you somehow use the, how we were talking earlier about dual energy and the presence of iron or not? Could you use that somehow? Yeah, I guess there's no iron anywhere. I'm kind of thinking through this with you a little bit.
Yeah, I'm wondering which kind of energy also, because organic matter are carbon
very low.
Yeah, it's very low.
But if it was phyllosilicate, it would still have silicon and oxygen, although you'd probably have oxygen in the carbonate matter too, the organic matter.
Yeah, it's also very low energy. So I don't know
that's true. Maybe a higher energy and then a very low energy. Okay. I mean, the other thing obviously that you could do is you could inject it with a highly attenuating noble gas in order to see if it's porosity or not.
Yes.
But that's super specialized. Okay, great. One last question. This is out of my domain. But you were showing that vein of the carbonate, and it seemed like there was some magnesium zoning. Is that correct? Or
yes.
What and that it was polycrystalline. What does that, do you have any thoughts on what that means? What does that tell you about the alteration conditions or its formation or what was happening as it was forming?
Yeah, this is something that is very kind of struggling, is that we observe this variation on the vein scale, but the vein itself is made of different grains. So it might means that we first create the smaller grains inside, and then we the carbonate vein starting to grow larger and larger, but changing with the fluid composition. And so I think we need more study on the thermodynamical conditions of precipitation of carbonates, and I have to more look on the previous studies. But maybe the fact that it's the opposite tendency of what was observed before, maybe it means that it's not the continuosity of going from silicate, phyllosilicates, and carbonates, as it is thought, or as it can happen for other study. But here it might explain the fact that it's a late event in which the fluid has all these elements, and then maybe the iron and siderate and rhodochrosite would form first and then change to magnesite. So it would be maybe the opposite tendency, depending of the availabilities of the cations. Yeah, that's your.
Cool.
Yeah.
Okay. Well, thank you. Very nice paper. And from what I could tell, dissertation looks great and a very nice presentation. And I'm done.
Thank you.
Thank you, Romy. Thank you now.
Okay, so a lot of my questions have already gone.
Sorry.
I will start the same as everybody else. Your presentation was exceptionally clear. It was very well designed. I particularly liked your voxels. It reminded me of Minecraft very much.
Or Rubik's Cube, it depends. My voxel is Rubik's Cubes and voxel Minecraft.
So I've got a few questions left. So one was about the coarse-grained phyllosilicates. You had a good picture of that. Coarse-grained phyllosilicates, and they have rather a unique texture. You could probably describe it as a meshwork texture.
A meshwork texture.
Yeah, you see that the coarse-grained phyllosilicates.
Yes.
There's what looks like a net, and the actual coarse-grained phyllosilicates are growing into voids off of wall structures. Have you any idea how that particular texture might
like this fibrous texture?
Yes, you can see they look like fibers.
Yes.
They're almost like Christmas tinsel. Yeah, you can see the little phyllosilicates growing off of them, and they're growing into void space.
Yes.
Have you any idea how that texture might? Sorry, I'm really putting you on the spot. You can tell I already know, can't you?
So how this texture can grow?
Yeah. So think about these phyllosilicates that are growing into void space. They're druzy, aren't they?
And why it's like this also?
Yeah, but they're clearly growing on those wall structures, that net structures, and they're growing inwards, presumably into a fluid-filled cavity. So the question is, how do you start with that net? What makes that net?
So the phyllosilicates structure.
Think about olivine. What olivine looks like down the microscope.
So it is following it might follow the crystallographic.
Well, you know when you look down an optical microscope olivine, you're a geologist, so you've done that. No cleavage. But there are structures within olivine. About what they look like.
For me, the olivine is quite like homogeneous.
So if you've got, let's say I've got an olivine with fractures in it, they've often got curved fractures, don't they? They have no cleavage. And then start altering that. What's going to happen?
So it will start to hydrate the olivine and to form phyllosilicate through the structure to the fractures.
Absolutely. So that makes a network structure. And then if you get rid of the olivine in between, then you've got those holes into which the phyllosilicate grow. So there's papers by Martin Lane on producing this kind of structure. So that these areas are probably altered olivines. Altered.
Well, that's funny because we observed on this side a very homogeneous. In the paper, there is this feature. So on the side here, you have a clear square like this, which is very homogeneous. And I was like, oh, this is an olivine. So I look at the mineral composition, but it was still phyllosilicate. So I was like, oh. But maybe it's a pseudomorph of olivine.
Absolutely.
And yeah. So it was my first thought.
And it's very rare for me to look at something and think, oh, I actually know what that is. So another question I had was about the fractures around your carbonate band. And this lovely, and that's an SEM from an SEM image. Did you see all those fractures in the XCT as well?
No, because they are very thin. Well, they are still 4 micron, so it's higher than our resolution and voxel size. However, in CT images and XCT, you have also one voxel has also the values of the surrounding voxels. So if you have a matrix or opaques, it will increase or decrease the voxels inside. So it's very hard to be sensitive in the CT images to very small fractures. But there are some that we observe, such as the largest one in the middle, or the largest one we could observe there.
Because in your CT slice up against the carbonate band, in your paper, you show what look like conjugate fracture sets that are planar at 2 different angles. And you mentioned that the carbonate vein was following those fractures. It's parallel.
Like this one. The parallel one. Yes. Yeah. They are following almost continuously toward all the grain.
So the reason I asked, this is a horrible thing for me to do, is that we had a sample of Ryugu, sample A180, which we did XCT on, and then we, like you, embedded it in resin to do SEM on. And after a while, we noticed fractures growing. So over time, as this thing is exposed to the terrestrial environment, it's put in resin, it starts to look like this. It starts to fall apart into, and you actually can see the fractures. They grow. The original fractures are there. They extend through fracture tip propagation. They start joining up, and then you start making these networks.
So also, I guess it's inside the matrix too.
Yeah.
Following the minerals.
Yeah. So it looks like the sample is contracting.
Yeah.
At room temperature. Slowly with time.
But what is funny here is that we have carbonates on both sides, as you can see by the white here. And here the carbonates are very, the fractures on the left side is very more important. So it might be also the result of the mineralogy itself. So maybe the little G3 mineralogy is more resistant to fracturing, more strong to resist to fractures compared to lithology 2. So yeah.
I'm glad you left this picture up because the follow-on question to this was something that I thought you were going to ask. But all these little sulfide grains inside that, is it just sulfide that are in there, or is there any matrix inside the carbonate vein?
There are some carbonate, some matrix, sorry, around what we observed as carbonate grains forming the vein.
Okay.
So there are some matrix around the carbonate vein. Sometimes it's fractures. So here on the right, it's fractures. But sometimes it's filled with phyllosilicates.
So I was wondering whether the sulfides in there had little areas of matrix with them, and whether they are little microxenoliths inside that vein, or whether they are phenocrysts from the fluid.
Yeah, because they seem to be randomly oriented.
Yeah. I would thought that first, because I'm talking about the late fluid that form carbonates, but they might have the fluid might have formed something else before also, like maybe sulfides, I don't know, and then form the carbonates at the end.
So if they are little microxenoliths, so the veins coming through and it's breaking off bits of matrix into that fluid, might those little microxenoliths tell you something about the emplacement of that vein? You imagine, here's the water of my vein, it's cracking through the rock, it's breaking up little bits of the matrix.
And then you have some phenocryst sulfides, for example, that...
Yeah, in that, what should happen to those phenocrysts, to those microxenoliths? How should they behave inside that vein? What would happen here if I took...
maybe find a...
I'm going to ruin your... But here's my little bit of xenolith. I'm going to drop it into my fluid. There it is. What happened to it?
It will react with the fluid, maybe.
Where is it in the bottle?
At the bottom.
At the bottom. Yeah. So are these all at the bottom of the vein?
Where is the bottom?
Where is the top and where is the bottom?
Well, they look to me as if they're in the middle.
Yeah.
Well, yeah, they look for me. They're in the middle. So
how could I get that in the middle?
The density of the fluid. Maybe.
Yeah. So if my fluid was more dense, but if that's an aqueous fluid, it's going to be about the same.
Or maybe it's not. That's my A0.
So you're a geologist. So think about this in terms of a dike, igneous rock. And I've got a xenolith, a mantle xenolith in it. Why is that mantle xenolith contained within that dike? What do I have to do? What does the dike have to do to keep that xenolith there?
I think it's the density of the fluid and the movement of the fluid.
It's got to flow, isn't it? It's got to flow fast enough to keep that up. And the speed it has to go is dependent also really on how quickly it cools or it crystallizes. Maybe this is some kind of flow indicators.
Yes, but how can you form, like what the thing that I'm wondering is the micro, like the crystallites, all the micro and subgrains that form the vein. It's not one unique fluid. I mean, it's one fluid maybe, but so there is multiple nucleation. So maybe it means that the fluid crystallized very quickly, and so you have multiple crystallites, multiple nucleation. So it's not it's very it would mean that it's a very dramatic event.
Or your zonation tells you nucleating inside of the vein units.
And maybe we can also find, I didn't look for it really, but if there is a fluid coming through the fractures, you can also take in your path, you can take the minerals that are located on the side and have a remaining shape, maybe of the sulfides that were on the side of the fracture. It's
So,
something
so,
like that.
so earlier we had the idea that, are these carbonate magmas rather than carbonate liquids? I don't think they are, but to put that as a question, so carbonate magmas are dolomitic magma. It's going to have a temperature of 700-800 degrees. So how can you tell that that is not a carbonate magma?
I think we have to look at maybe some morphologies, the morphologies of the grain at a smaller scale, maybe TM. So this is something that could also impact the temperatures. I mean, the temperatures can impact the TM analysis of the grain.
There is a more geological way. If your magma is at 700 to 800 degrees C, what might you expect to find around that vein?
What would we expect to find what?
What would we expect to find around the vein?
Some melting or like structure. Yeah, melt structures, heating, dehydratations on the side.
Yes. And we don't see it.
No.
So it can't be a carbonate magma.
Yeah.
It has to be an aqueous fluid. Well, shall I stop there? Very impressed by the way you answered the question. Thank you.
Thank you so much. So I think it's my time now. Yeah. So we try to be short also because all the questions have been taken. So I wish to congratulate with you. When I see the title, I say what I can ask. Finally. And I'm really impressed of what we can do with the tiny grains and which kind of analysis we can do. It is indeed a very precious material. So I think you do something new. This non-destructive technique, I think, will have a good perspective with new samples that will come back or that we have already in hands. And still a few questions. So about fracture, actually, how can we distinguish between primordial ones and the ones that are produced by the spacecraft on the way from to Earth? You have any idea? Or? Because it's a very fragile material.
Yes, that's true. So there are fractures that are that we observe from, for example, here. You observe that there are carbonates that kind of follows the fractures. So it means that some of the fractures were happened before the carbonate precipitations. And is it true? It's true that we cannot. It's hard to decipher between the fracture that was made after, for example. But what we can look also, it's some precipitation of other fluids, because it has been observed also. If you have a fractures and then there is another fluid that arrives, you will kind of either precipitate other minerals, phyllosilicates, or you can also dissolve other the fractures ring. Yeah, I think the precipitation and further precipitations help us to attribute these fractures to made on the parent body. But I'm not 100% sure that there is all fractures are not from all the shaking from coming from Japan to here, and however there are still around this vein and not on the right, and I don't know, there is this very weird dichotomy between the fractures distribution.
And maybe please go back to the slide, the very beginning where you show the parent body of Ryugu.
This one?
Yes, this one. Hard life, isn't it, for Ryugu?
Yes.
So I read in your manuscript that there was a collision of about a 12-kilometer size projectile with a 100-kilometer parent bodies. So this is the origin of the Unalia family. And I wonder which kind of energies are in place in this kind of impact. So I did a short calculation with the kinetic energy and I was impressive. And which temperature was experienced during this impact? And I think it was several thousands of degrees.
On the parent body for the description.
Yeah.
I remember the plot of Nakamura, and I cannot remember the temperatures, but it's probably hundreds degrees and few gigapascals too.
So my question is how organic matter that has been found on Ryugu, maybe not in the grains that you analyze, or maybe yes, we don't know, finally can survive to this high temperature. And why you do not have a huge dehydration?
Because it is thought that the Ryugu asteroid is made from fragments that are coming far from this impact point. So it is quite not very easy to imagine. But if you have a parent body, there are simulations that so you hit your parent body here, but what is ejected is from the opposite side of the parent body. And this is why we do not observe a lot of dehydratations and minerals and a lot of features that shows that the parent body of Ryugu suffered impact or heavy impact. So that would explain that the fragments are coming from the other sides of the parent body, and so didn't record this event, except few grains, maybe.
Okay. And if you go to slide 25 or 26, so you have a huge heterogeneity in composition of the different lithologies. So I'm not an expert of this technique, but which are the error bars and how you can distinguish among different grains? You have an order of magnitude or?
Compared to other grains? Or
compared to what you showed there, which are the typical error bars?
Here so it's the scanning electron microscopy, and it's very difficult to obtain the compositions for lighter elements. So what I did in my manuscript is to attribute a percent of error on lighter elements and then less error on the heavier elements. So here is the percent the error bar. I mean it's the uncertainty, sorry. And what I did here is that I just applied an arbitrary uncertainty for these elements. But so, and I say it also in my manuscript, is that we have to be careful with the proportion of each element here. What I really want to insist on is the tendency of this distribution and elemental composition.
And I'm still astonished by the variation of composition you may find. So usually I work from remote sensing, so we see a lot of grains together, actually from telescope or from spacecraft. Even if you take Ryugu, you have a spectra that from the orbit are completely are different from what you found on grains, on different kind of grains. So I wonder if you are a space agency with a lot of money, which kind of instrument you will put on your orbiter to do your best and study the mineralogy.
Orbiter,
Yes,
not in situ.
or maybe in situ.
That's true that we can do also a lot of on using spectroscopy. We do observe the tendency, and this is also what we wanted to do at the following, is to link these lithologies with spectroscopy. So if I had a lot of money,
Devoted to space exploration.
Yeah, I don't know. Yeah, I would do in situ analysis, more local, I think.
But which kind?
yeah.
You will drill and do whatever.
Drill. drill. No, I think, yeah. Well, because I like lithologies, I think I would drill to have more chance to observe differentiations, and we could also observe the like, yeah, I don't know, spectroscopy on drills, maybe, or mineralogy. Lot of money. We can do something with it. No.
I think about for the future. I think we take you a lot of time, so we stop here with the questions, and I give the floor to directors. So I start with Rosario.
So let me thank the colleagues that accepted to join us at this committee. Thank you very much for joining. So it was a real pleasure. And thank Léna, and congratulations to you for your work, 3 years with us. Let me say a few words for the committee to put this into context. So Léna arrived here. She was coming from another university. She was not master student with us, which means that she had to face the first challenge when she arrived, which was joining a group that she didn't know, learning new techniques, learning new science questions, addressing new science questions. And this was very fast. And she was very quickly involved into the measurements. The measurements arrived very early, which is good on one hand, but it also means that she didn't have much time to actually set both into the science questions. So this was, I think, it was a challenge, and we managed. And other challenges arrived. I think you very quickly realized that there was a little bit of this effect of, like, Dahar said, "What are you doing here?" Right? As a geologist, a geophysicist in a lab of astrophysicists, sometimes it's not an easy life. And having 3 supervisors can also be a challenging experience, especially when the 3 supervisors speak different languages and use different techniques. So I think we were brave and we managed to accomplish this. More difficult times arrived during the thesis, and we discussed a bit about that. So I don't really say how brave we were to face all that, and finally, okay, my colleagues would say maybe more words about some specific aspects. One thing I want to say is that the PhD thesis is also a student that becomes a scientist, and this happens in a lab of people, and it's been very nice to see how you joined the spirit of the lab and how much you gave to everybody, and also how you managed how you asked for help when help was needed. That was very human, and I think it's beautiful. It's something beautiful to see. So for the future, I wish you, of course, all the best. But there are 2 things that come to my mind when I think of you, and one is curiosity, and the other one is a free spirit. And then in a home, you keep that, and you learn little by little how to focus that and use that as the energy to accomplish your future. So thank you very much for the opportunity that we were supervising the 2 years and the time spent.
Thank you. So, thank you, Léna. Thank you also, all of you for your questions. And so I wrote it.
Me too.
It is with emotions, and I saw you given your Ph.D. You remember yesterday evening I sent you a texto, and I was thinking about you, and it was the end of 3 years for us. So just to remind what we propose you a PhD subject with major technical developments, requiring a good understanding of X-ray, tomography, and important programming skills that I don't have, and the ability to manage a large set of data. So you succeeded in overcoming all the challenges, and then you had to develop a method to section a grain using Parmi and using this technique. And then you had only 1 year to finish everything else, and also to obtain more classical technological data on the 2D section. So it was really a PhD that demanded a lot of motivation to get all this, to get through 2 years of the technical development, not to be depressed. And also, so you show a lot of determination in overcoming all these kind of difficulties, plus what we know. So I was really impressed by you. And in fact, you impressed me even more in the final months of your PhD, because in a very short period of time, I will say for 5 months, I don't know that's it, you managed to propose a scenario by yourself for the brain's formation, and to get into the more, I would say, cosmochemistry part of the work. And you did that really rapidly, and so I was really, really impressed. So really congratulations. So you can really be proud of what you did, really. So it is providing for the future. So it was 3 great years of collaboration, and bravo. Thank you. And I will finish by joining Rosario and Alice in congratulating for the great work you accomplished. And thank you for sharing this journey with the 3 of us. It was not always easy, but we did it mainly because of your quality as a scientist, but also as a colleague. And Rosario and Alice already say a lot in English, so I will switch to French for more personal things. So pour moi, ça a été le premier encadrement et ça a été un honneur de le faire avec toi. Une thèse, c'est jamais facile, c'est la date d'exception. On t'a mis au milieu de plusieurs techniques difficiles à appréhender, et dans ce bazar-là, tu as su te débrouiller. Tu as fait un travail énorme, tu as développé une nouvelle méthode. Tu m'as beaucoup impressionné. Je t'ai pas arrêté là, tu as mis au point de nouvelles techniques de préparation. Tu as aussi été un appui pour beaucoup de gens dans le labo, pour beaucoup de gens qui sont dans la salle aujourd'hui. Donc, ça a été énorme tout ce que tu as apporté au labo, tout ça au milieu de problèmes techniques, humains, mais aussi plus personnels. Donc, encore une fois, ça ne fut pas simple, mais tu as été impressionnante tout du long. Il y a eu un certain nombre de « on paniquera plus tard ». Merci d'avoir osé et merci de nous avoir fait confiance et d'avoir paniqué plus tard. Merci beaucoup. Parmi les choses que j'admire beaucoup chez toi et qui m'impressionnent, il y a ta résilience, ta volonté de faire, ton courage, et ça rejoint ce que disait Rosario, ta capacité à défendre ce en quoi tu crois, ton esprit libre, ne perds pas ça. C'est très important, je pense. Et heureusement que tu avais tout ça, parce que tu as survécu à une thèse avec 3 encadrements, une thèse à 3 têtes. Et il fallait de la persévérance et un esprit libre pour nous résister. Donc, bravo. On t'a vu grandir, on t'a vu devenir une scientifique avec un profil unique, à cheval entre astrophysique et géologie. C'est important pour la communauté qu'il y ait des gens comme toi qui existent et qui s'expriment. Donc, je suis ravie que tu rejoignes la communauté des scientists et que tu rentres parmi nous en tant qu'adultes, si je peux dire, c'est que le début pour toi. Je suis sûre qu'il y a plein d'autres choses extraordinaires qui t'attendent. Des petites découvertes, des grandes aventures, des ratés, plein de choses. Mais fonce, ose, vas-y, te censure jamais. Bon, je crois très fort en toi. Et n'oublie pas de y aller paniquer plus tard. Voilà. Après, j'arrête. Donc, encore merci pour tout ce que tu as fait, tout ce que tu as partagé avec nous. Et on a hâte de voir la grande scientifique que tu vas venir. Merci. Léa.
Si je demande, s'il y a quelqu'un parmi le public qui soulève un doctorat, qui a une question pressante. J'espère que non. Bon. Donc, le jury va aller dans notre salle pour délibérer. So, for the member of the jury, we switch to the others.
Yeah, for the Romy and Frederick, you have to go to the next
other
Zoom.
donc, au vu de la qualité de la présentation et des réponses, les jurys te félicitent. Pour ton travail et te décernent à l'unanimité les titres de docteur en astronomie astrophysique de l'Université Paris.
Thank you very much.
Nous t'invitons à prêter serment.
On something. So I can say it in English or in French.
As you wish.
I will.
You should say.
So I'll say it in English to conclude on this English presentation. So, in the presence of my peers, with the completion of my doctorate in astronomy and astrophysics, in my quest of knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. So nice. So thank you, everyone. So now I think it's time for the acknowledgement. So thank you. That's it. First, all bets are open. I think, well, we already saw something. So who's gonna cry first? My mom, Zelia, or me? I don't know. First, I would like to thank each member of the jury for agreeing to come and examine my thesis, defense, and dissertations. Thank you very much. I hope you enjoyed my defense as much as I enjoyed to do research for the last 3 years and for the past 3 years. And I will be very happy to be one of your colleagues for the following years. And then, sorry, my English friends, but I will switch and continue in French. Ensuite, donc, par où commencer? La fin, c'est-à-dire merci à mes parents pour m'avoir aidé à préparer le délicieux pot qui nous attend après, et les galettes, voilà, représentent la Bretagne, ou le début, et donc merci à mes parents pour avoir créé et initié et éduqué cette chose étrange que je suis. Grâce à vous, je suis là aujourd'hui. Merci pour votre aide qui m'a aujourd'hui permis d'arriver au bout de ces 8 longues années d'études au cours duquel j'ai su prendre mon temps et visiter le monde aussi. Donc, je pense que c'est ma mère qui a gagné le pari. Voilà. Et comme l'éducation ne se fait pas que par les parents, merci aussi à mes frangins, tous deux présents ici, qui m'ont toujours soutenue, quoi qu'il se passe, même dans les moments les plus sombres de mon existence. Lol, n'en parlons pas, s'il vous plaît. Ouais, Lola, merci, vous êtes les meilleures nièces que j'ai jamais eues. Et j'espère que vous m'avez fait un beau cadeau, un beau dessin. Et j'en ai vu déjà un, c'est super. Ma famille de manière générale qui me suit peut-être ou qui suivra ma conférence sur... Enfin, ma conférence, ma soutenance sur YouTube. Ma ponos, tout cela va. Ensuite, bien évidemment, il y a les potes de la primaire à l'université qui vous joignent au cours de votre route et qui sont toujours là pour vous soutenir. Du coup, j'ai Malalou, qui est aussi mon tic ou mon tac, ça dépend. C'est tic et tac. Il y a Flo aussi, Yo et Laure. Merci d'être là aujourd'hui et d'être venus nous soutenir. Et merci à ceux qui sont en ligne, qui n'ont pas pu faire des déplacements. Merci aussi à mes anciens professeurs de Nantes dans le master Géol et Planéto, car ils ont su me transférer leur passion et surtout ils ont su me faire réaliser à quoi pouvait bien servir une équation. Parce qu'il faut savoir que moi, au lycée, en économique et sociale, j'étais loin de me dire que j'allais étudier les astéroïdes en ayant détesté la physique, désolée, et la chimie, désolée les autres amis, dès le collège. Je ne pensais pas qu'un jour je terminerais docteur en astrologie, en géologie, comme j'aime appeler ma spécialité. Comme quoi, avec un peu de motivation et de volonté, on peut faire quasiment tout ce qu'on veut. Du coup, j'ai fini par atterrir là, à l'Institut d'astrophysique, encadré par... ces 3 énerves humaines.
Et là, ils m'ont vu arriver, vivant dans un camping-car, à moitié rasé, à tébaté. Ils ont dû se dire, waouh, c'est toi les énergies humaines, c'est pas nous. Du coup, merci de m'avoir fait confiance. Merci de m'avoir accompagné, de m'avoir vu galérer et soutenir. Rosario avec tes en commentaire. Alice avec tes abonnements aux urgences. J'ai jamais vu ça. Et Zélia, la seule personne qui vous dira pendant 3 ans, on paniquera plus tard. Et qu'en 10 minutes, elle rentre dans votre bureau et vous dit j'en ai marre, je veux rentrer chez moi, t'as 10 minutes pour soumettre ta thèse. Et là, bah, on panique. Mais bon, c'est pour 10 minutes, ça va. Non, sincèrement, merci à vous trois. J'ai adoré faire ma thèse avec vous. Et c'est grâce à vous aussi que je suis là aujourd'hui. Et donc, merci aussi à toute l'équipe, Astrochimie, Planéto, pour l'accueil, les rencontres. Merci aux anciens, Tania, Elsa, Max, Jans, et aux actuels et stagiaires passés ou présents. Spéciale dédicace à l'équipe technique des petits chats là, qui sont ici. Merci Laura pour avoir dit aux gars de ne pas faire la perceuse à 14h. Merci à l'équipe optique, électro-dépôt, techno, et spécifiquement Nico pour les soirées terre. Lionel pour m'avoir permis d'écrire ma thèse dans un jacuzzi. Et puis Pierre-Maurice pour les sessions escalade. Un grand merci à tous les doctorants. J'ai bientôt fini, vous inquiétez pas. À tous les doctorants, un plus passés présents pour leur accueil chaleureux, les soirées jeux, bowling, laser game, paintball. D'ailleurs, paintball quand vous voulez. Et bien sûr, je ne peux pas partir d'ici sans avoir remercié Sacha quand j'ai changé de bureau. Merci à Jean d'ailleurs pour avoir du soleil. Je ne pensais pas que j'en découvrirais un autre soleil. C'est une force, un exemple sur beaucoup d'aspects, personnels et professionnels. Du coup, merci de m'avoir accompagnée et soutenue pour ces derniers mois où j'étais un petit monstre. Et voilà, parce que je voulais juste travailler, mais ce n'est pas possible. Enfin, merci évidemment à Maniac, Marius, mon poteau, connu sur un parking à l'Euro Merlin, il y a 2 ans, mon coloc, mon frérot, mon padré, parfois aussi, ça dépend. Mon aventure sans toi aurait toujours été plus fade et clairement plus nulle. Et tu as toujours été là tout le temps et j'espère que tu seras encore là pendant mon post-doggy dog, comme tu les appelles. Voilà. Et donc, enfin, et je vous promets que c'est la dernière, merci encore à vous, famille, vous, amis, vous, doctorants, vous, équipe, vous, labo, pour votre soutien à la fois psychologique et aussi, ça a été financier. Un moment particulier de ma vie où, à un moment tout feu, tout flamme, à un moment donné où vous vous rendez compte que si vous n'avez pas tous ces gens qui vous entourent, bah, en fait, vous n'avez plus rien. Donc, merci à vous tous de m'avoir soutenu pendant ces derniers moments de ma vie. Oh non, de dernier. À vrai dire, c'est les derniers moments. C'est les derniers moments jusqu'à maintenant. Ouais. Voilà, désolée, c'était un peu long, mais je n'avais pas. Ah, c'est bon. Et bah, maintenant, je vous invite à aller prendre et boire un petit apéro, fêter ça comme il se doit. Et merci encore à tous. Et oui, merci. Oui, merci aux gens en ligne, bien sûr, mais c'est bon. On va continuer. Ah oui, c'est vrai que vous ne pouvez pas venir boire l'apéro avec nous, malheureusement. You cannot come and drink something with us, unfortunately. So, Romy, I hope the morning wasn't too harsh for you. And thank you very much, and I hope that we can see around a real glass always someone.
Yes, I hope so. Good job. Congratulations.
Okay. Merci. Ah, c'est là la différence. Merci à vous.